And we're on to the last talk of the session, where Thomas will tell us about another CakeML extension.
Touch wood. That looks like progress. I can't see what I'm doing. Sorry, 1 second. Do I have a... Oh, come on. Sorry, 1 second.
Let us know if we should summon an AV expert to help with something.
Yes. Here's my key press for that. Come on. Really? Okay. Oh, hello. Okay, hi everyone. I'm Thomas. I'm here to talk about dynamic computation in CakeML. This is joint work with a different subset of the CakeML team. As you might have heard already in this session, CakeML is a verified implementation of an ML language, essentially a subset of standard ML. And this is a talk about putting the eval feature in. What on earth does that mean? Well, this is a feature you might have seen before, if you can possibly read the screen. This is a read eval print loop, or an interactive verification, an interactive programming environment. It's one in which you can type a little snippet of program and have the system evaluate it on the fly. In this case, the CakeML compiler is compiling those tiny little silly snippets of program I've written there. You can do this yourself. So this runs on my laptop. You can fetch it from CakeML.org. It's now a standard feature of the CakeML compiler. Currently, it requires x86 and Linux for silly reasons, but this is the feature we're building. Yes. Can you hear me more clearly now? Whoa, okay. So this is now a standard feature of the CakeML compiler, and you can launch it in this read eval print loop mode, and you'll be able to experiment with writing a little program interactively. So there's two reasons we do this. Firstly, let's make it clear, this is a talk about adding eval to CakeML. We add a primitive to the language. We add this runtime feature to the compiler, so the compiler can compile new programs at runtime, and we use that to verify, in a limited sense, that REPL you saw. And because CakeML is already a very big project, we try not to change everything too much. So we try to keep the existing verification structure. Why would we do all of this, though, is essentially another project. This is an interesting verification exercise itself, but also the whole 4 theorem prover that we're verifying all of this in, and some other theorem provers, use eval-like features of their host functional languages. So in particular, we're interested in the candle theorem prover, which is a different project. It's essentially whole light ported to CakeML. That uses Eval to run user tactics, and it comes with a proof of correctness. It's a theorem prover which is proven down to the binary to only prove true theorems. So that's pretty cool, and this would be an ideal talk for this kind of verification and proof assistance sort of track. But today you're going to hear about how we put Eval into the compiler, which perhaps belongs next door. But the existence of this motivates the kind of work we're doing. So in the CakeML project, we like theorem provers. We're using a theorem prover for everything, but we also want to, in principle, support theorem prover technology with this programming language. So before we got started on this, CakeML was an ahead-of-time compiler, and it's self-hosting, so it builds itself. You can write CakeML as both a function and as syntax in the CakeML language. And so in the slightly nonsense syntax I've printed there, you can apply CakeML to itself. And that makes sense in at least some interpretation. Okay, we want to add an eval mechanism which can evaluate new programs which appear in a CakeML environment at runtime. We can think of evaluation as compilation plus execution, and anywhere where we're running eval, anywhere where eval appears, we should be able to run the compiler because the compiler is itself a CakeML program. So the big idea here, which gives rise to this project, is maybe we can just make eval execute of compile the program. So call the CakeML compiler and then execute that. What does execute mean in this context? Not all that much. Sorry, this is either really loud or really quiet. What does execute mean here? It means, for the moment, just stick the new machine code right next to the existing machine code and call into it. We're not using a linker, and so it's all a little bit of a special case. And it's partly because we don't want to go back and rerun the design, replay large aspects of the CakeML verification. Okay, so that's the implementation we're trying to build. It's not that complicated. What about the proof? The biggest single issue comes from the design of the compiler. I don't know if you can see the little arrows there, but the compiler is a long pipeline of a collection of little transformations. There's 30 or more of them. This is a simplified, anonymized version of a diagram which Magnus maintains on CakeML.org, which gives you a map of the compiler and tells you what all the phases do. You would not possibly be able to read the text. But the pipeline consists of 30 plus phases, each of which has its own proof of semantic simulation in some sense or another. So each one of them is going to preserve the observed behavior of the program that it's compiling, and then the correctness of the compiler is just the composition of all of those proofs. Okay, so here's the problem. If we're doing one of those proofs, and we need to show that a program, compilation of a program simulates a program, in the case where that program is this new execute operator we're thinking of introducing, what does that mean? We're expecting that execute is basically going to fall through the compiler pipeline, so we're going to introduce the compiler early, and then we're going to push execute down towards the kind of place where machine code makes sense. So if we're somewhere in the middle of the compiler, execute is trying to run a program, but it's got that program represented in a representation that we can't really understand at this level. Right, so what program are we running? And we could consider doing some things in the implementation to keep the original program around for longer. We hit some problems towards the end of the compiler pipeline that you're in now a very low-level program, which is neither a machine code program nor a good place for writing a compiler. We'd need to decode, by this stage, late in the pipeline, everything's down in memory. We'd need to decode aggressively in order to get back to the source level values, and the existing simulation proofs don't promise that we can do that. So that would be a giant headache. We need some kind of a trick, and the trick is to add an oracle. So the oracle is a gadget which just conjures out of its own private knowledge, or who knows where, knowledge of what program you're trying to run when you do an execute. So the semantics of execute turns something like get the program that we are trying to execute from the oracle, popping it from the sequence of programs that the oracle knows about. Fetch a compiler, also from the ambient semantics. Try compiling the program using the compiler, the pure compiler in the state, and check that the program that we're actually trying to execute, the concrete one that we're handing around, is the program that the oracle and the compiler would have given us. Okay, it's a little bit fiddly, but this is going to effectively unwind the compilation enough that everything works. So the oracle can see the future, it knows what programs we're going to compile. This compiler is called a checking compiler, and these things only appear in the semantics for the purposes of the proof. They don't affect the way the program actually works or the compiler actually works. And the point is, each intermediate representation has its own oracle, so when we're in this situation where we're trying to figure out how does execute simulate itself, the two oracles give us back two explanations of this program which differ by application of the compiler phase that we're at. And so in fact we fall back to the kind of situation that we should be in. We continue, it will be the inductive hypothesis that the programs that we fetched will continue to simulate each other. Okay, so this is the conceptual design from fairly early in the project. The implementation is pretty straightforward. We're just going to introduce the compiler as soon as we can and then push the problem down to the back end of the compiler. And the proof is going to work by introducing this oracle to basically undo that symbolically, just enough that we can pretend that the compilation was being done a bit at a time. All right. That was the ideal design. And then by the time we verified it, this project ran for years, the design got a little bit more complicated. So in order to explain all of that, I need to tell you just a little bit more about the CakeML compiler than I have up to this point. And I'm trying to do this as minimally as possible because I've given longer versions of this talk and we can be here forever. So a very few minimal details about the CakeML compiler. The CakeML language has namespaces. So it has module operations and other ways of manipulating namespaces. You can shadow constructors, you can shadow values, etc. The CakeML compiler has to be stateful, and annoyingly, the CakeML compiler can fail to terminate. It can fail to, not fail to terminate, it can fail to produce a program. So it can just produce an error because something was too hard. So it's an early phase that's responsible for getting rid of namespaces by assigning things global IDs. So we give everything global unique IDs, so if there are two Fs, you can always tell them apart. That's one of the phases that's going to need state. For instance, it's going to know what the next free ID is. And towards the end of the pipeline, we see some phases that can do things like try and place machine code at particular addresses and discover that it just became too hard somehow. I don't know much about the back end of the compiler, so I don't even really know why that is. But the compiler can fail. Okay. Because of that, that means that that substitution that I showed you about 5 slides back is going to get a bit tricky. Right? We want to introduce the runtime version of the compiler where we see an eval, but it's going to need the state because it needs to compile programs the same way as the ahead of time compiler did. And so the state's got to somehow get here, possibly by being loaded from a file. It needs to know, okay, that's an obvious detail, but it needs to know which namespace to run the program in. And it also needs some way to say, suppose the compiler failed, what do we do? And the simple answer is, this nice design got too difficult. Instead, we're going to say that any code which is using eval has to call the compiler itself. So the REPL is actually going to do the call to the compiler itself. That means that it can take care of issues like deserializing the compiler state from a file. It can, well, obviously it can specify which namespace the program runs in. And finally, supposing the compiler fails, the REPL can then just directly report that to the user rather than some primitive trying to tell you what's going on. So the real eval operator actually has 6 arguments. The first is the environment or namespace value, and the third one is the program you're trying to run. There's input and output compiler states, and then there's the output compiler code, which actually has 2 parts. Okay, so what's going on here? Essentially, we're doing the checking compiler thing again in the language semantics. So having called the compiler for real, you now interact with an abstract version of the compiler that exists in the semantics only, and it's going to check that the input-output pair we're seeing here, so the first 3 arguments, the input to the compiler, and the last 3 arguments, the output of the compiler, agree with what the abstract compiler said says the compiler function is. The reason we're doing that is that you called the compiler yourself, and we need to prove that you called the right compiler. And then the semantics ignores most of the arguments if that succeeds and just evaluates the program in this environment, and the compiler ignores most of the arguments as well and basically just treats this as execute of the final arguments. So that's how we manage introducing a dynamic program, having that be valuable in the semantics, and also have that make sense in the compilation of the language. Okay, typo. So env identifies a namespace. These get created by a new primitive, which we have to apply. And then there's the problem that env maps names to values of different types. So we can't compile that into something that we can feed directly to the compiler. So instead, you have to identify envs by number, and you tell the compiler the number of the environment, and then these numeric IDs can be revealed by yet another primitive, and as long as the actual compiler was called with the ID of the environment that the semantics understands, everything is fine, as long as they count the same. There's a bit of a complication here, though. One of the headaches that Eval introduces is that the order of execution of the compiler is now quite different to the order of execution of the semantics. So we have a program on the left that's going to do an eval. The compiler will have compiled the entire program, but the semantics steps through the program one declaration at a time, and will at some point leap into the right-hand side program and do all of that before getting back to the remainder of the original program, which means that the compiler for eval, the runtime compiler, will execute everything will see everything on the right after the ahead-of-time compiler, but that's a different order to the semantics. We can fix this for the purposes of environments just by using two-dimensional IDs. Okay, what about the proof? There's not that much time left, but I should tell you about the interesting part of this project, or the big challenge of this project. The CakeML proof is pretty big now. I think I counted it at about 320,000 lines of whole 4. That's putting it up there, not as big as SEL4 or CompSort if you include all their variants, but pretty big, with a substantial part dedicated directly to the compiler. And the eval project had to modify about 50,000 lines of code of that, assuming we measured it correctly. And this is despite the fact that we tried not to make big changes to the redesign. So there's quite a lot of proof engineering had to happen in this project. And I'm just going to give you some flavor issues here. You could write a very boring textbook. So the compiler proofs were updated in reverse order. We started at the back end of the compiler and worked upwards. The Oracle design was designed to make sense so that execute could be stitched in at the very bottom level. And in the low-level phases, it works pretty well. It gets a bit more tricky when we get up to the earlier phases. For instance, many of them distinguish between declarations and expressions, as I talked about, but eval and execute are expressions that can introduce declarations. They have to be because something like candle wants the user to be able to introduce new types. And that means that some inductive proofs that were previously two inductions now have to become a mutual induction. That's the kind of thing that shocks people. It's not actually the biggest problem. You mostly just need to concatenate the relevant proofs. But a related problem that's harder to really put your finger on and explain to you, but is a headache, is that compiler order issue I showed you before gets exposed in eval, that some inductive proofs that are following the declaration order can no longer assume that the compiler is in sync. Okay, this is exactly the kind of proof project where it's possible to make a mistake, go in the wrong direction, and not figure that out for far too long. Here's the silliest of them. We introduced an oracle type, which is an infinite sequence of both compiler states and programs. And at the very end of the verification, we need to create the oracle, and we made it a complete infinite type. But what happens if the user only calls eval finitely many times? We can invent new programs. That's fine, it's easy to invent a dummy program, but can we invent a dummy state satisfying all the invariants? Not necessarily. We could just run the compiler, but the compiler can sometimes fail. And in the end, we finessed that. Now, I'm out of time, so I'm going to flip through to the summary and say, we finished the verification. How do we go? We're at a golf course. I give us a pass score. The design mostly held up. The implementation had to be tweaked a bit. And the Oracle-based strategy worked, but there were headaches that we had to cope with. Let's skip that and just say, in conclusion, this is CakeML with eval. This is for putting the I in ITP in a verified theorem prover. Find candle at cakeml.org, play with it, and any questions?
Any questions from the audience?
Everyone is too terrified for questions.
I can kick us off with one. You showed us one of the relations that's used to structure the compiler proof, where you have an oracle, and then you, within the relation, call the compiler itself. That compiler there is a pure Hall function, or what is it exactly?
So you're asking about the dynamic semantics of performing execute is you use the oracle to ask, I think this will be the correct slide, is you use the oracle to ask what program are we really trying to run, and then you compare the compilation of that to the bytes that you actually had.
Right.
Sorry, what was the question?
So that compiler that you retrieve here is a CakeML program?
That compiler only lives in the state. So the operation for popping a program out of the oracle and the operation for looking at how the abstract compiler works or the checking compiler works, those only live in the semantics, and they only live in the ghost part of the semantics. So they're used for assertions, but they're not used for the actual dynamic behavior. So the point is to try and carry, so we had the user in the source semantics run the compiler, and we're trying to carry the evidence that the bytes we ended up with are the compilation of the program you're trying to execute bit by bit as we go through the proof pipeline.
Okay, so does it make sense to ask if that compiler could itself use eval and the proofs would still work?
No, so that compiler needs to be a pure function.
Okay.
And in fact, the CakeML compiler needs to be a pure function. It can't, for the moment, do any evals. Eval never types, for instance.
Got it.
Yeah.
Okay. Go ahead.
If I was doing a clean slate version of this project, do you think the approach with the oracle is the right structure just in itself, or was that more about making it easy as an addition to the existing proofs?
So this is one of these funny questions. I've put a bit of work into making the oracle approach work. I didn't come up with it, actually, and I'm a little ambivalent about it. It depends on the fact that the semantics is deterministic so I don't know how to do a multi-threaded version of this for the time being. Maybe there's some ideas. But what's the alternative? I don't have any fantastic ideas there either. Yeah. There are things that we would do differently if we did a clean slate implementation. So I kind of waved at some headaches. We explained some of them in the paper. And one of the reviewers came back with, at the end, you're just saying that these unique IDs need to be different. It wasn't that obvious. And often, if the phases that were the problem were right next to each other, yeah, it'd be obvious. There's no way that we'd have missed that. But when they're separated by a whole lot of other context, it's easy to make these kinds of mistakes. Yeah.
All right, let's thank the speaker again.